Hey everyone, let's talk fluids and pressure. So first and foremost, what even is a fluid? What do I mean when I say fluid? It's basically just something that doesn't hold its own shape, so by itself it doesn't have that sort of a form, and it can be easily deformed by small forces. So this can refer to both gases and liquid. The main rule is if it flows, it is a fluid. Think about a cup of water. If you slap it, it's going to change shape. That's what it means by easily deformed. Now, pressure is something that we associate a lot with fluids. And it's basically that even in a static fluid, and this is one that does not seem to be moving overall, a glass of still water on the table, a container of some sort of gas that's closed, and it doesn't look like the fluid itself is moving anywhere, but the individual particles consistently are. They're moving all over the place and bouncing into each other, and, more importantly possibly, they're all bouncing against the outer surface. Now, as they bounce against the outer surface, this causes the gas or liquid or whatever it might be to exert a net outward force on the surface, just because of all these collisions that happen consistently. So the average force is just defined, average pressure is just defined as the amount of force per surface area of the fluid. That's it right there. So what are the units going to be of this? Well, if it's force per unit area, it's going to be in newtons per meter squared. This is also known as a pascal of fluid. So pressure itself is a scalar, just pascals is just a number, but the force that describes it is a vector. A lot of times you'll find pressures reported in terms of atmospheres, where one atmosphere is 101.3 kilopascals. This actually represents the average pressure on Earth at sea level. I'll talk about that in a bit more detail in just a second. Now, as a general rule, fluids flow from high to low pressure. Imagine that I took a bunch of you all, put you in a small room, and had you blindfolded and just had you run in whatever direction you happen to be facing at the moment. You're going to slam into each other. Eventually, someone's going to get knocked out of the room if the door stays open. And typically, no one's going to come from outside the room in, because they're going to just get knocked back outward as soon as they do. But you will get an overall flow from that tightly packed room of high pressure into a more open space with lower pressure. So I said I'd mention a little bit more about the atmospheric pressure, 101.3 kilopascals. That's equal to 15 pounds per square inch. So think about how many square inches you have on your entire body. That's a lot of force. Now, we don't feel crushed about it because the fluids inside your body are pretty close to 1 atmosphere as well. Now, this is why we'd get in trouble if we went way down deep underwater without any sort of a protective pressurized suit on, or way up high if you're not inside a pressurized cabin of an airplane, for example, because you want the fluids inside to be about the same as the fluids outside to keep an equalized pressure that way. So I mentioned static fluids. If we talk about the weight of the fluid being negligible, the pressure throughout the fluid is just constant. That's because these little particles are just bouncing off in every direction, so it's constant everywhere. Now, if the weight is not negligible, like water weighs a lot. If you've ever carried a big bucket of water, that's pretty crazy. So the pressure varies at different locations. Think mountain peaks versus the ocean floor. Now, this change in pressure depends on a fluid's density, and as you all probably know from a previous physical science class, density is just mass per volume. It's denoted by the Greek letter rho. Now, if you're at a different depth, you can calculate the new pressure. Now, in this case, the pressure is going to be a lot bigger down at the bottom because you've also got gravity pulling down on all these particles. So on average, you'll have more collisions down low simply because of gravity. And I can find the new value as the old value, which in this case, since it's open to the air, I've got a big open bucket here. That's 101.3 kilopascals, or 101,300 pascals, plus rho, the density of this water or fluid or whatever it might be, times g times h. Where h is just the height, the difference in height between my two locations. And that's about that. Now this brings me actually to Pascal's principle, which says that a change in pressure at any point in a fluid is transmitted everywhere through the fluid. This is especially helpful in hydraulic lifts, as pictured below. If I put down some force F1 on the small piston, then I'll get a new force F2 out of the big piston. And there's no conservation of force, so since the areas are different for the various pistons are cylindrical, so their cross-sectional area is a circle. And with different radii for these cylinders, I get different cross-sectional areas, therefore I get more force out. So I can put something like a car on the big lift, push down with not too much force, not an unreasonable amount for a person, and I'll be able to lift up the entire car, simply because all of this fluid is confined in this space, so a change in pressure over here is the same as the change in pressure over here. Another thing I'd like for you all to know is about Archimedes' principle. The basic idea is that there was a king who asked Archimedes to test whether the crown that he had made was actually pure gold. Archimedes thought an easy way to do this would be to measure the density, but since it's an irregular solid, he can't just do a simple equation to measure it. So he was stuck for a bit. The answer finally came to him when he took a bath. He found that if he dunked the crown, the volume of an object submerged underwater is equal to the volume of fluid that it displaces. So if I put 0.2 meters cubed of something inside water, then the water that I push upward will equal 0.2 meters cubed in volume. Not only that, a fluid exerts an upward buoyant force that's equal to the weight of that submerged fluid, which actually tells me whether objects float or sink. So the only cause of a net acceleration is a net force. So if something is going to float upward, that just means there's got to be an upward force. That's what's called the buoyant force. That's going to be equal to rho GV, where rho is the density of the fluid, v is the volume of fluid the object displaces, and from Archimedes' principle, this means it's also equal to the submerged volume of the object. So not only do you have that upward buoyant force, you've also got the downward force of gravity. So if the buoyant force is greater than the gravitational force, that means the displaced fluid weighed more than whatever the object is you put underwater. It will accelerate upward. If the buoyant force is left, it will accelerate downward, and if it's equal, it will remain suspended in place. Now, from the previous slide, I mentioned that V is equal to the submerged volume of the object. So a lot of times you'll see an object floating where a portion of it is submerged, and it's just sitting there. That means this underwater volume, when you displace this much water, it created a buoyant force equal to the downward gravitational force. Cool. Another thing I'd like for you all to know is the continuity equation for fluid flow. So if you're going through a chamber, your fluid going through some sort of a chamber, the cross-sectional area, which again for a cylinder is a circle, times the velocity at one location is going to equal the cross-sectional area times the velocity at another location. And this seems kind of backwards, because if you've ever been in, let's say in school, when a ton of people are leaving, they're all crowding into the hallway, and if the hallway gets narrower, they move a lot more slowly. It's not so much the case with gases. Think about it, try this at home. Get a garden hose or something like that, turn it on, then put your thumb over a portion of the opening, and you'll see the water just come flying out at a much faster speed. That's because of the continuity equation here. We've got the Coanda effect as well, which is if air is flowing over a curved surface, so the upper solid lines represent the flow of the fluid, and the object itself is curved like that. Do they go straight off, or do they curve and bend and follow that path? It's actually the curving idea, and we'll talk about why that is actually in class, but I'll have a fun little demo for you. Another effect we're going to explore is the Magnus effect, and this is just saying that a spinning object moving through a fluid will curve as a result. And you see this in soccer. I love watching, right now I'm on a Javinko kick. If anyone watches Major League Soccer, he plays for Toronto. And Javinko can curve the soccer ball like nobody's business. In baseball, that's how a curveball works. In tennis, if you give it top spin or bottom spin, it'll curve up or down. So we'll look into the mechanics of that in class as well. Then there's the Bernoulli effect. There's a mathematical equation involved that I usually like to teach. This semester we're just running out of time, so I'll only ask you about it qualitatively, and that's this. As a fluid flows, the faster the fluid moves, the lower its pressure. I added horizontally in here just to indicate, this doesn't trump the, the idea that fluid lower in a container has more pressure that we talked about earlier. So this doesn't, supersede that. But in general, the faster the fluid moves, the lower its pressure. Right? So as a general reminder, fluids flow from high to low pressure. Fluids are at a higher pressure the closer they are to the center of Earth because of gravity. An object submerged in fluid displaces a volume equal to its own volume. That's just good old Archimedes. Pascal's principle tells me that a change in pressure in one location is the same as the other. F1 over A1 equals F2 over A2. I'll use this a lot for hydraulic lifts. And the continuity equation as a fluid is moving, A1 V1 equals A2 V2. The cross-sectional area that it's traveling through times its velocity stays constant. The effects that you'll need to know and we'll explore in class will be the Coanda effect, that fluids follow the path of a nearby surface. It's actually a really interesting mechanism as to why that happens. I love talking about it. So we'll definitely talk about it. The Magnus effect means spinning objects will curve in a fluid, and the Bernoulli effect, fast fluid gives you low pressure, slow fluid gives you higher pressure. All right, so we'll explore this and more next time I see you.